Good morning to one and all. Myself, Nagajyothi, working as an assistant professor in Department of ECE in MLR College. So, in the last session, I have discussed about determination of a transfer function by using a block diagram reduction technique. So, in order to determine the transfer function by using a block diagram, we need to remember some rules. That is how whenever the blocks are in cascade, what is the rule, and if the blocks are in parallel. So without remembrance of rule, you cannot determine the transfer function by using a block diagram. But whereas in this session, I am going to discuss about determination of a transfer function by using a signal flow graph. So in this case, the outline of the session represents what is the signal flow graph technique and how to convert a block diagram into a signal flow graph, and determination of transfer function by using a Mason's gain formula, and some problems related to the signal flow graph. So the first thing is, what is meant by a signal flow graph? As the name itself indicates, a signal flow graph is a graphical representation of the relationship between various system variables. And in case of signal flow graph, no need to have remembrance of any rules as that of the block diagram. Instead of that, we'll be using a direct formula. That formula is known as Mason's gain formula. Why the name has been given as a Mason's gain formula is it has been developed by Mason. That is the reason the formula which we are using in order to determine the transfer function is called as Mason's gain formula in the signal flow graph reduction technique. So in this case, if in the given question the question is determination of transfer function, but instead of giving a signal flow graph, if they have given us a block diagram, we can able to transfer, or we can able to change a block diagram reduction technique into a signal flow graph. So signal flow graph can be obtained from the block diagram reduction technique, or you can directly draw the signal flow graph also. Signal flow graph can also be directly obtained from an equation. So in this, you can draw the signal flow graph in two ways. One is converting a block diagram into a signal flow graph, or the second way is they'll be giving an expression. From that expression, you need to draw the corresponding signal flow graph. So the equations must be written in an algebraic form. As we know that a transfer function is defined as Laplace transform of output to input. Whenever we are saying a term called as Laplace transform, that itself indicates it is in S domain. So, and the other more important thing is this signal flow graph is having a limitation which is basically used for linear systems only. That is, it is applicable only for an LTI systems. So as seen to that of the block diagram reduction, in case of a block diagram reduction, we have seen the components are block, summing point, takeoff point. In the same way, there are some components in the signal flow graph. The components in the signal flow graph is, the first one is node. So how can you define a node is, if a signal is the signal which is represented in terms of a variable is nothing but called as a node. So a point representing a variable or a signal is called as node, and the node is represented with a circle or a dot. And basically there are three types of nodes. One is input node, output node, and mixed node. The name itself indicates input node. So whenever a signal is where it is starting, that particular point of starting point of a signal is called as an input node, and where it is reaching to the destination point, the last output of that particular signal is nothing but called as an output node. And coming to the mixed node, a node in which it consists of inputs as well as outputs. So this input node is also called as source node, and in case of an input node, it consists of only the outgoing branches. So if a node consists of only the outgoing signals from that particular node, so this particular node is nothing but called as an input node. So you cannot get any signal to this particular node. So input to this particular node is 0, but there may be consists of n number of nodes from that node. This is nothing but called as an input node. Coming to the output node is also called as a sink node, in which it consists of only the incoming branches. So here, this, let me take this is a node. if for this particular node there are n number of signals coming to this node, but after coming over here the signal will not be able to transfer to the other node. So this is the last point of a signal where it need to be reached. That point is nothing but called as an output node. Coming to the mixed node, a node in which it consists of both the incoming signals as well as outgoing signals through a branches is nothing but called as a mixed node. So now let me take a node. Let me take this node is A, this node is B, and this node is C. If you observe here, coming to the node A, from node A we are having only the signals going out of the A. So this node A is called as an input node. From node A we are having only the signals passing out of node A, but there are no incoming signals to the node A. That is the reason this node A is called as an input node. But if you observe the node B, this node B consists of an input signal coming from node A as well as some input signal coming from D point. After coming over here, again it is transferring to the node C. So as B node consists of incoming as well as outgoing branches, it is nothing but called as a mixed node. But whereas coming to the node C, after coming the signal to the C, it is not transferring any other. So this is the last point where the signal is going to be stopped. So that particular node is nothing but called as an output node. So an output node consists of only the incoming branches, but there won't be any outgoing branches. So what is meant by a branch is, it is a line segment which is connecting or which is joining between the two nodes. So in order to join node A and node B, I have drawn a line. This line segment is nothing but called as a branch. And this branch consists of two parameters. One is gain and the other one is direction. So the signal passing from one point to the other point will indicate whether it is an input node, mixed node, or a output node. But if it is multiplying with a corresponding value, that particular value is nothing but called as a gain. So for every branch there consists of two parameters. One is gain and the other one is a direction. Direction will tell you the branch is terminating at which node, and the gain will tell you what is the transformation from input towards the next node. Now let me consider the example. So in this case, it consists of nodes y1, y2, y3 and y4. So the nodes present in this signal flow graph is 4 nodes. Those nodes I am representing here as y1, y2, y3 and y4. If you observe here the node y1, from the node y1, the signal is transferring from y1 to y2. So this y1, it is transferring only from y1 to the other nodes, but there is no branch which is entering into the y1 node. That is the reason y1 node is called as an input node. Similarly, if you see the y4, in case of y4, the branch is entering to the y4, but it is not leaving from the y4. That is nothing but y4 is called as an output node. But if you observe this y2 and y3, in this y2, one is incoming node from y1 and the other is also an incoming node from y3. So here there are two incoming nodes. That is one branch you are getting from y1 node and the other branch you are getting from y3. Similarly, after getting at a point of y2, it is leaving from y2 to y3. So as it consists of both input entering as well as leaving, this y2 and y3 are called as mixed nodes. And if you observe here, this is a branch. On this branch there is a direction. This direction itself indicates the signal is now flowing from y1 to y2, and along with this you are having a gain. The gain between y1 and y2 is A. So in this example of this signal flow graphs, there are gains which has been represented with A, B, C and minus D. So the next component is a path. It is a route of connected branches in the direction of branch of arrows. So here path is nothing but, in simple words we can say that how the signal is going to be transforming from one node towards the other node is nothing but called as a path. In this path, the direction gives a very significance in which it will show whether it is an entering into the node or leaving of the node. That is the reason it gives the clear cut idea how the signal is moving from one node towards the other node. So in case of the path, the direction indicates or it will give you whether that signal is an incoming signal or an outgoing signal. And if this path may be open path or forward path. So if what is meant by an open path is a path starts at one node and ends on the other node. So here this is a path in which the signal is going to be started at node A and it is ending at E. After reaching node E, again it is moving towards the Y. So the transferring of a signal from one node to the other node is nothing but called as an open path. But what is meant by a forward path is it should start at an input node and end at the output node. So in the previous figure, y1 is an input node and y4 is the output node. So the path between y1 and y4 is nothing but called as an forward path, and the path between y1, y2, y2, y3 and y3, y4 is nothing but called as an open path. So how can we distinguish between an open path and a forward path is, in case of open path, it is not a compulsion that the signal need to transfer from input to output. The signal may transfer from input to intermediate nodes and stop over there. But whereas in case of a forward path, definitely the signal need to move from the input till it reaches towards the output. And the next path is nothing but closed path. The other name for the closed path, it is also called as a loop. So what is the name itself indicates closed path. So a path should start from a node and it should end at the same node. So starting point and ending point of that path is at the same, then it is nothing but called as a closed path. So if you observe here, the path is starting at, let me take, this is node A, this is node B. So this is one branch, the gain of that branch is G1. After reaching towards the node B, again it is going back towards the A. So starting point is A and the ending point is also A. That is the reason it is called as a closed path. And whenever a signal is moving from A to B, the corresponding gain is G1. Whenever the signal is moving from B to A, the corresponding gain is G2. So the loop gain, loop itself indicates closed path. So multiplication of those branch gains is nothing but a loop gain. So for this figure, the loop gain is G1 into G2. So how can we define a loop gain is, it is a product of branch gains and it will give you the information how the branch is going to travel from which node towards the which node. And coming to the third one, non-touching loops. So here a loops with no common nodes. So now let me take, this is A, B, C, D. So if you observe here, the first loop is starting from A and ending at B. After reaching towards the B, again it is going back towards the A. Coming to the second loop, it is starting from C to D. Again, it is moving from D to C. So, AB is one loop, CD is one loop. But if you observe in these two loops, there is no common node. So, if you doesn't have any common node between the two loops, then such loops are nothing but called as non-touching loops. Now, so these are the components of the signal flow graph. So a signal flow graph basically consists of nodes. These nodes may be an input node, output node or a mixed node, and connection line between the nodes is nothing but called as a branch. And the next one is loop, that is path. Path is nothing but how the signal is going to be transferring from one node towards the other node. This path may be either the open path or a forward path. The difference between open path and a forward path is, in case of an open path, the signal may travel from input to any intermediate values. It is not a compulsion that it should end at the last. But whereas in case of a forward path, the path should travel starting from starting node and it should definitely end at the output node. That is nothing but called as a forward path. Coming to the next one, loop. Loop is nothing but a closed path. The signal should start from one node and it should end at the same node. Then it is nothing but called as a loop. Non-touching loop is nothing but if you don't have any common node between the loops, then it is nothing but called as a non-touching loop. So these are the basic components which are related towards the signal flow graph. And the second is how to convert a given block diagram into a signal flow graph. So as we know that in case of a block diagram, each subsystem is represented with a block. So in this one, let me assume that the input for a system is R of S and the output of a system is C of S. And the block or a subsystem is G of S. So if you want to represent this in terms of a signal flow graph, this input is represented with the input node. That input node I am mentioning it as R of S, and output C of S is represented with an output node C of S. And the signal need to transfer from R of S to C of S. As I told you, whenever the signal is moving from one node to other node, it is represented with a branch. So I have drawn a branch in which the signal is moving from R of S to C of S and the corresponding gain is nothing but G of S. Similarly, if you observe here, it consists of input R of S, output C of S, forward path gain is G of S, feedback path gain is H of S. Already in the previous sessions, I have told you what is meant by forward path gain and what is meant by feedback path gain. If we are giving output, some part of output towards the input, it is nothing but called as a feedback. So here I am representing this E of S, this summing point signal as in one node, R of S signal as input node, C of S signal as output node. So this is R of S input signal, summing point which is represented with a node, and C of S. So here R of S is an input node, C of S is an output node. As in this figure, the some part of output is given back towards the summing point. This summing point have represented with a node which is nothing but E of S. So output of C of S is again given back towards the E of S. And we know that in this summing point may have both the symbols same or different. If you are having feedback as negative, then it is nothing but called as negative feedback. That is the reason this H of S gain is represented with minus H of S. So if you observe here, this E of S consists of a branch coming from input as well as another branch coming from C of S. After entering, it is again going towards the C of S. So this E of S consists of two incoming branches as well as one outgoing branch. That is the reason this E of S is called as a mixed node. So now let me give you some thing how to draw a signal flow graph. As I have told you just now that a signal flow graph can be drawn by using a block diagram, or the second one is by using an algebraic expression. So let us consider some algebraic equations. So the first equation is y2 is equivalent to a1 to y1 plus a4 to y4. So if you observe here, all these five expressions which I have written over here, all these are algebraic expressions, and this y1, y2, y3, y4 and y5 will represent the nodes. So in this case, I'll be having total how many nodes? I'm having all completely of 6 nodes. Those 6 nodes are y1 to y6, and whatever the branches, this a1, a12, a23, a53, all these are branches. So depending upon this, we need to draw this a12, a21 will give you what is the gain of that particular branch. Now if you observe here, this is y2. So let me take this is a node. This node is y2. This y2 node is an expression of a1 to y1. That itself indicates I am having a y1 node over here. From y1 node, the signal is coming to the y2 with a gain of a12. and along with this it has been written that plus A4 to Y4. So I need to get Y2 from the other side. What is other side? Let me assume that there is other more node here, Y4. This Y from the Y4 I am getting into the Y2 with the corresponding gain as A42. So this is how to draw an expression, or in simple I can draw in this way. This is Y2 which is an output node. For this one, this is Y1, this is A12, and at the Y2 only I am getting other more A42 with the corresponding node as Y4. Similarly, for Wi-Fi, output node is Wi-Fi, the inputs are Y4 and Y3. So this will be the input for the Wi-Fi also. This can be drawn in this way. So the signal flow graph for Y2 is equivalent to, as I told you, the complete, if I observe all these expressions, I am getting complete of 6 nodes. So just I have represented Y1, Y2, Y3, Y4, Y5 and Y6. Coming to this Y2, this is Y2. This is a combination of what and what? It should get the signal from Y1. This is a signal from Y1 and the gain for that is A12. Along with this, this is a Y4. I need to get other more signal from Y4. The gain for that corresponding is A42. Similarly, Y3, this is a Y3 node. What are the inputs for the Y3? One is Y2 and the corresponding gain of the Y2 is A23. Similarly, the other input is Y5. From Y5, I am getting till Y2, the corresponding gain is Phi3. So if you combine all those things and if you draw this, this is the overall signal flow system graph. So in this case, for each expression we are drawing it individually, then we are combining all them into a single graph, that is nothing but called as a signal flow graph. So according to our syllabus, no need to draw the signal flow graph from the algebraic expression, but they'll be giving a signal flow graph. From that signal flow graph we need to determine the transfer function. So the main aim of this topic is determination of a transfer function by using a signal flow graph, in which we are using a formula which is nothing but a Mason's gain formula. So what is the Mason's gain formula? Is the overall transfer function can be written as sigma of k equal to 1 to n pk delta k by delta. So here what is meant by pk is nothing but path gain. How many number of forward paths is there? We need to write down the path gain for each forward path, and k represents for the given signal flow graph how many number of forward paths are there, and delta will give you determinant of the graph, and delta k is, suppose let me take, there are two forward paths, so k is equivalent to 2. In that you can write down delta 1 as well as delta 2. So the transfer function can be written as 1 by delta p1 delta 1 plus p2 delta 2. So here p1 is first forward path and p2 is second forward path, and delta is nothing but the path gain which is not touching to the corresponding paths. That I'll explain you with one example. So now let me take this is a signal flow graph which is given. If you observe here, this signal flow graph consists of how many nodes? 6 nodes. The nodes are represented with a numbering 1, 2, 3, 4, 5 and 6. The first step in case of a signal flow graph is we need to check how many number of forward paths are there. The name itself indicates a forward path is nothing but a path which will give you information about how the signal is going from input node towards the output node. So here in this case the input node is 1 and the output node is 6. If you observe here, I am having a path, or I am first traveling from 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6. So I am having a first forward path in which the signal is moving from 1, 2, 3, 4, 5, 6. Just see the path gains. What is the gain between 1 and 2? 1. Between 2 and 3? 1. So just multiply the path gains. So forward path gain is 1 into 1, 1, 1 into G1, G1 into G2. So the first forward path gain is G1 into G2. Similarly, check, do you have any other paths where the signal is starting from 1 and it should end at the 6? So if you observe here, there is a path 1 to 2, 2 to 3. After going 3, instead of going 3 to 4, it is going directly from 3 to 5. So second forward path is P2. The signal is moving from 1 to 2, 2 to 3, 3 to 5, 5 to 6. Means, can I say this is the way how the signal is transferring? This is 1, 2, 3, 5, 6. Between 5 and 6 the gain is 1. Between 3 and 5 minus G3, 1, 1. So second forward path gain is minus G3. So in case of step 1, first determine how many number of forward paths are there. Similarly, draw the corresponding path gain. So in this first path, just it is a straight line of all the nodes. 1, 2, 3, 4, 5 and 6. This is 1, 1, G1, G2, G1. For each step you need to represent in a diagrammatical manner. So the first forward path is G1 and G2, second forward path is minus G3. And the second step is you need to find out how many number of loops are there. So if you observe here, as I told you previously, this loop is nothing but a signal should start from one node and it should terminate at the same node. So if you observe here, this signal is starting from 2, 2 to 3, 3 to 4. After reaching 4, again it is going back towards the 2 only. So, and look, is there any other loops in the given question? If you observe here, it is going for, after going 3, it is directly going for 5. But it is not going back towards the 3. So, in the given question, it consists of only one loop. What is that loop? That loop L1 is nothing but starting from 2, 3, 4, 2, 3, 4. After 4, it is going back towards the 2. And see the what is the expression? 2 to 3 gain is 1, 3 to 4 is G1. 2 to 3, 1, 3 to 4 is G1. And between 4 and 2, it is minus H1. So the loop gain is 1 into G1, G1, G1 into minus H1. So loop gain is minus G1, H1. Similarly, see, is there any other loops? No. After finding out the loops, the next step is you need to find out the non-touching loops. As in the given question, there is only one loop. We cannot have any non-touching loops. So the number of non-touching loops is 0. Now coming to the next one, we need to find out the transfer function. So the transfer function is pk delta k. As I told you, in this question there are two forward paths. So I can write down this as transfer function is equivalent to 1 by delta sigma k is equivalent to 1 to n. So here n is number of forward paths. As I am having two forward paths, I can write down this as 1 by delta p1 delta 1 plus p2 delta 2. So now the question is, you know what is how you have find out p1, how you have find out p2. The unknown things are what is meant by delta 1, what is meant by delta 2. In order to find out the delta 1 and delta 2, see the forward path, see the p1 path. In case of P1 path, as it is covering all the 6 nodes, do you have any loop which is not touching any node? As it is covering all the nodes, the delta 1 is equivalent to 1. But if you observe here path 2, which is a missing node, 4 is a missing node. Do you have any loop which consists of only node 4? There is one loop. What is that loop? 2, 3, 4 and again 2. But along with 2, 3, 4, along with this, along with 4, you are having other nodes also 2 and 3. So delta 2 is also is equivalent to 1 because we don't have any loop with only node 4. So how will you determine this delta 1 and delta 2 is depending upon the forward paths which you have drawn. If there is any missing node, observe that missing node, and if you have any loops corresponding to that missing node, that will give you the delta value. As in both these cases, as there is no loop which is made with only 4, that is the reason delta 1 is 1 as well as delta 2 is also 1. Coming to this, so now I got the value of delta 1 as well as a delta 2. Coming to this, the unknown value is delta. This delta is nothing but 1 minus sum of individual loop gains plus sum of two non-touching loops minus sum of three non-touching loops plus so on. That is alternate sign. First is minus. First you need to write down the individual loop gains. Second is plus sum of two non-touching loops. This is the symbols need to be minus plus alternate symbols, minus plus minus plus, and you need to increase the loop gains. First is individual, second is two non-touching, third is three non-touching. Coming to our figure, as I told you that we consist of two paths P1 and second path P2, and we have calculated delta 1 value as well as delta 2 value. Delta 1 is equivalent to 1, delta 2 is also equal to 1. Coming to the P1, the P1 gain is we got as G1, G2 and P2 is minus G3. This is P2 is minus G3 and P1 is G1, G2. And we are having only one loop. What is that loop gain? That loop gain is minus G1, H1. As we are having only one loop, we doesn't have any non-touching loop. So this can be written as G1, G2. This is nothing but P1 into delta 1 is 1 plus this is P2. P2 is nothing but minus G3 into delta 2 is 1. 1 by delta. What is delta? 1 minus sum of individual loop gains. Only one loop. So this can be written as G1, G2 into 1 is G1, G2 minus G3 by 1 minus. Then in the expression we are having minus. This sum of individual loop gain I have got it as minus G1, H1. So this can be written as minus G1, H1. So this can be written as G1, G2 minus G3 by 1 plus G1 H1. This is how to determine the transfer function by using the Mason's gain formula. Now, just I'll generalize this. Now, if you observe here in this, it consists of nodes. This is R is input node, C is an output node. And by leaving this input and output node, I am having a number 1, 2, 3, 4. So, the total number of nodes are 6 nodes. And if you observe here, in how many ways my signal is going to be transferred from input to output. The first path is a straight line which is from R 1, 2, 3, 4, C. This is 1. This is G1, G2, 1 and 1. And the second path is I am having a signal from in which I can R is going till 1. After 1 it is reaching to 4. Again it is going to C. So this is gain is 1. This is G4. So for this path 1 gain is G1 dot G2. This is path 2 with the gain of G4. And if you observe here, there is a path or a loop from it is starting from 2 and ending at 2 itself. So it is one loop. And the second loop is, it is starting from here and ending it here. So it consists of two closed paths. One closed path is G2, G3, and second closed path is G1, G2, and G5. So if you draw this first path, 2, 3, this is G2 and this is G3. So the first path, closed path is G2, G3. Coming to the next one, starting from 1, 2, 3, 4. 1, 2, 3, 4. Between 1 and 2 it is G1. Between 2 and 3 it is G2. Again it is 1. And again it is coming back to 1, which is nothing but minus G5. So the path gain is, closed loop path gain is minus G1, G2, G5. So from this we need to calculate next. So if you observe here, in this the nodes are 2, 3, here also 2, 3. As there are common nodes, there is no two non-touching loops. And coming to the next point, we need to calculate delta 1 and delta 2. If you observe the first forward path, as it is covering all the nodes, the delta 1 is equivalent to 1. But if you observe here, which nodes are missing? 2, 3 nodes are missing. Just see that, do you have any loops which consists of only 2 and 3? So we are having a loop which is nothing but forming a loop by combination of 2 and 3. So from this I can write down delta 2 as 1 minus of this loop gain. What is this loop gain? G2, G3. So I can write down the first forward path is G1, G2, and delta 1 is 1. And I am having a second forward path. That forward path gain is G4. And if you observe the second forward path, as there are missing nodes are 2 and 3. By combining 2 and 3, I am having a loop. That loop gain is G2, G3. So delta 2 is equivalent to 1 minus G2, G3. As you know that the Mason's gain formula is P1 delta 1 plus P2 delta 2 by delta is 1 minus sum of individual loop gains plus sum of two non-touching loops. So here sum of how many loop gains I am having? 2 loop gains. What are those 2 loop gains? One is G2, G3, second is minus G1, G2, G5. So G1, G2 into 1, P2 is G4 plus G4 into 1 minus G2, G3 by 1 minus 2 loops are there. The loop gains are, one is G2, G3 plus minus of G1, G2, G5. So this can be written as G1, G2 plus G4 minus G2, G3, G4 by 1 minus G2, G3 and plus into minus, minus, minus of minus plus. So 1 minus G2, G3 plus G1, G2, G5. This is the overall transfer function for the given signal flow graph. So this is the way how we can determine a transfer function by using a signal flow graph. So thank you. This is the end of Unit 1 of Control Systems.